Hi everyone, I'm Ben Chaffin. Great to be back here at the gathering. Just a note about that title slide. The thing at the top is a 13-piece dissection, so that's the same 13 unique pieces making G4 and the square and the 13. And that is not my exchange gift because I made one and it's way too hard and it's no fun at all and it's a terrible puzzle. But it was a lot of work, so I wanted to show it somewhere, so there it is, and don't worry, you never have to see that again. It's been a great conference so far, a lot of fascinating presentations with deep connections across fields, a lot of fun. Unfortunately for all of you, this is not such a presentation. This presentation is about something completely pointless with no redeeming mathematical value at all. So I was looking something up in the Encyclopedia of Integer Sequences last year, and I typed it in wrong, and I got this instead. I love the OEIS, like one wrong digit, and you're just down the rabbit hole. So this is the first power of 2, which has a certain number of zeros in its decimal expansion. So 2 to the 10th is 1024 that has 1 0 and so forth. And it was known up to the 18th term, which is a large power of 2, and you'll have to take my word for it that there's 18 zeros in there. And I thought, well, I mean, this doesn't seem very hard, right? I mean, you just write the number down and see if there are any zeros. I mean, it's trivial. I'll do this during lunch. But it turns out to be a little harder than that. So converting that number from binary to decimal takes about an hour, even with a really good base conversion algorithm. So you can't do billions of anything if they each take an hour. So you're going to have to get faster than that. But fortunately, I had some help. So here's some cool stuff that I wish I had thought of first. So first of all, if you're looking for something in decimal, don't work in binary. Binary to decimal is division, and division is hard. I certainly never understood how to do it. So work in base 10 or something close to it. The second is, so now you've got this really big number and you're sort of doubling it over and over, looking at the powers of 2. Long strings of zeros are not going to sort of pop in and out of existence like some quantum foam or something. They're going to sort of emerge and they're going to kind of grow and shrink over many doublings. And that's great because it means you don't have to look at every power of 2. You can sort of skip along and look every once in a while. And if you find kind of a medium length run of zeros, then maybe you have to do some more work to figure out maybe it used to be bigger and you have to rewind, or you can inch forward and see if it's growing or something. But you don't have to look at every power of 2. So a nice choice of parameters turns out to be work in base billion, American billion, 10 to the 9th, and multiply by 2 to the 34th. So look at every 34th power of 2. That's nice for a couple of reasons. So first of all, a billion times 2 to the 34th just barely fits in 64 bits. So you're making great use of your 64-bit computation. And you can show that if there's going to be a run of 18 or 19 zeros in there somewhere, you'll always see at least 11 of them. And that means that one of your base billion digits is going to be less than 1,000,000, which is only one chance in 1,000. So most of the time, you can very quickly see that there are no zeros around here, or not very many zeros around here. And only one time in 1,000 do you have to do any more work to sort of count how many there are. So that's good. But when you actually implement this, it's a nice collision of a beautiful theoretical algorithm and a real computer, which messes everything up. It doesn't actually perform maybe as fast as you thought that it was going to. And the problem is that, so you're multiplying this number and kind of digit by digit, and you have to propagate the carry from one digit to the next. And that means that everything you're doing depends on the thing that came immediately before it. And that's not how modern CPUs are designed. They're designed to do lots of independent things in parallel at the same time. And they're really good at finding things in your program that can be done independent of each other, but not if you give them a list of a billion things which all have to go in order. You end up using this just kind of a very narrow slice of your big, wide, fast core, which hopefully came from Intel. Little ad there. So how do we fix that? Well, don't do it in order, right? Make it parallel. So we divide the number up into chunks, and I'm going to multiply this digit, and then this digit, and then this digit, and then this digit, and then I'm going to, round robin my way through that and kind of fan my computation out across this whole big number. And now the thing that I'm doing doesn't depend on the thing that I just did immediately before. It depends on something that happened a while ago, and that's okay. And that turns out to be a significant optimization. It more than doubles the speed of the computation. And then, you have to sort of glue together your sections, and it gets a little complicated, but that's fine. So after several months on several computers, out pops 2 to the 11 billion, and you can read the rest. And that is a big number. In digits a millimeter wide, it reaches almost exactly from where I live in Portland, Oregon, to here in Atlanta. That was a nice coincidence. And here is the number. And I'm low on time, so I'll skip the next 63,000 slides. And there it is. In the middle of that number, or actually quite close to the beginning, a run of 19 zeros. I found it. And that is the most useless thing that I have done in the last 2 years. Thank you very much. Enjoy the rest of the day.